हवा नहीं है रुकते इसलिए ठीक है इन्हों लगा दीजिए। तो फिर बड़ा कैमरा मेन थोड़ा आगे करते हैं मेन एकदम बड़ा नॉर्मल। अच्छा साउंड दिख रही है साउंड लगा दे बस देखने एक्चुअली ये तो रिकॉर्ड ही होगा फिर फ़ोन करेंगे चेक करना हमारी मिस करें।
that time? What time? Huh?
non-trivial, slow accumulation and various two-dimensional methods have proved valuable. Well, earlier assignments were based on of high-field instruments, shift reagents do not work for the analysis, and therefore this is abundant. With the recent sensitivity, with the recent advances in technology and development of new techniques, sensitivity of carbon-13 has enhanced to the extent that determining carbon-13 coupling constant in natural abundance is possible. You know, it becomes carbon-13 has got a natural abundance of 10 to the power minus 2, whereas carbon-13, two carbons in the same molecule, the probability becomes 1 in 10 to the power 4. Then phosphorus again is a very useful nuclear. It is 100% natural abundance, spin half, T1 moderate. It offers several advantages due to simplicity arising from large chemical shifts, easy decoupling from other nuclei, and less number of atoms per molecule. So the number is less, so the spectra are not complicated. But application-wise, due to rich coordination chemistry, it plays a central role in numerous systems, including biochemical and biomedical and medical purposes. So very, very useful to study proton. Very, in medical science, very much useful. Biological and medical applications, they have grown dramatically after 1970. They deal with the structure of enzyme complexes, phosphoprotein, DNA, RNA, biomembranes, metabolic studies, and disease dissection and treatment monitoring, because the spectrum becomes very simple and recording is very easy and gives a lot of information without any typical modification. Then nitrogen. Now this nitrogen has two isotopes which are NMR sensitive, nitrogen 15 and nitrogen 14. But nitrogen 14 has got a quadrupole moment. But still, nitrogen 14 was the first nucleus, the very first nucleus, which led to one of the first discoveries of the chemical shift by Proton, Proctor and Yu. Very first besides all that. Because sensitivity of nitrogen 14 shift to structural changes, the reason is it's in the context, the structural changes are enormous compared to small changes in structure. So we are very useful for structure. Nitrogen 14 has become a diagnostic tool for the study of coordination, chelation, protonation, conformation, stereochemistry, and the solution equilibria and other dynamic processes such as ligand exchange, intermolecular motion, and tautomerism. So large number of applications, because these shifts are large and they are very sensitive to the changes in the structure. That makes it. Biological applications have grown dramatically. They deal with structure of enzyme complexes, phosphoproteins, DNA, RNA, biomembranes, metabolic studies, and disease dissection and treatment monitoring. You know, if a disease takes place, the structure of the molecule responsible for the disease changes, and that can be very easily detected using you are going in the wrong direction. Nitrogen 15, though the natural abundance is small, but it's spin half nuclear. It's an important nucleus to study the current with the current instrument and isotopic enrichment. Either isotopic enrichment and fairly sensitive instruments are available, then you can really study in the natural abundance. During recent years, many investigations of biopolymers have been made using nitrogen-15 shift, involving an indirect rather than direct detection via 2 and 3-dimensional NMR. And you know, if you take these spectra, 2-dimensional, 3-dimensional, you can get very useful information. Now, halogens again. Halogens other than fluorine have all large quadrupole moment which have virtually precluded their high resolution studies in covalent compounds. Most studies have thus been made on halide ions or other highly symmetric ions. So the line broadening effect or the quadrupolar effects are reduced because of the symmetry of the molecule, and they behave more or less similar to the spin half nuclei. So sensitivities and natural abundance for several isotopes of chlorine, bromine, iodine are reasonably satisfactory so as to enable studies of concentration ranges both to chemical and biological problems. Fluorine is the best NMR friendly nucleus, natural abundance 100%, spin half, and order of magnitude larger chemical shift than proton, and its coupling constants are also very large. So though it could give the complex spectra, but the chemical shifts are, so usually the first order analysis can be made, and does not need very highly sophisticated instrument. It is one of the very important elements from the point of view of its applications in chemistry, since it is capable of combining with many elements to give wide variety of compounds. Therefore, applications are numerous. Then noble gases, they are really noble due to their simplicity and symmetry. Noble gases have found particular use in development and testing of various theories. Now, you know, the substitution of the presence of a noble gas does not change the structure, so they are very useful in developing theories. Helium-3 and xenon-129 are spin half, while xenon-131 has quadrupole moment, as do neon-21 and krypton-85. Argon has no magnetically active isotope, so that cannot be studied. But others, because of their non-reactivity and structure like symmetric structure, they have found large number of applications, particularly in theory development, because when you want to develop a theory, you don't need that any structural change should take place. So there, I think they have found numerous applications. Then alkali matter ions, lithium, sodium, potassium, rubidium, cesium are all of central importance to biology and biochemistry. They have found great applications. Sodium and potassium are essential for normal functions of plants and animals. Lithium finds its importance for growth of some special plants in treatment of diseases such as psychiatric disorders. So the disease and the specific drug development has also found much application of lithium. Except for lithium, which has a strong tendency to form covalent bonds, the chemistry of alkali metals essentially ionic. So since they are ionic, they become symmetric, and therefore they are useful and easy to study, and no special effort is required. So it is used to study solvent-solute interaction, ion-ion interaction, which are of prime importance in biochemical study. For nuclear properties, you can see these are given the various nuclei of alkali metals, the frequency at which they occur, the natural abundance, and spin and all that. So these become very useful indeed. These are the frequency. Lithium, as I told you, behaves like a spin half nucleus because a small quadrupole moment. Still, lithium NMR in solution was observed only in 1976, and there is a special theory, a special story behind it. Why was it so sensitive and nice nucleus? Why was it discovered so late? Felix Valley actually performed some experiments. These are those days when continuous wave, you have to sweep the frequency in order to observe. So on the oscilloscope, he just observed a signal, but then he could not repeat it. He tried hard, could not repeat it for quite some time. So he got frustrated and left, went home for lunch, and after lunch when he comes back, he sees a beautiful signal. It was finally discovered, it was because of the large T1, large spin lattice relaxation time in G2O solution, and this was found to be 17 minutes at 80 degrees centigrade. So this was the reason why he could not repeat this signal once he saw so easily. And then finally, this is how it was discovered. And the applications are enormous, particularly in medical sciences and of course in complexation studies. Now, useful conclusion, what type of information can be derived? Change of shielding as a result of halide ion indicates that alkali halides have a partial covalent character which increases in going from fluoride to iodine. The change of sodium lineage with different salts indicates the utility of NMR in ion binding. Studies in different solvents have been utilized for investigation of preferential solvation phenomena in mixed solvent systems. Structure, dynamics, and kinetics of weak complexes of alkali metal ion. Alkali ion interactions with bases like adenine, thymine, and nucleoside like adenosine. Sodium-23 NMR is used to study cells and living systems with the help of paramagnetic shift reagents, say red blood cells, frog skeletal muscles have been. The ionic shift reagents remain in the outside of the cells, affect only the chemical shift of the extracellular sodium. The resonances due to intra and extracellular sodium could be well resolved, which could not be resolved without the shift reagent. So you can find out the environmental of the extracellular and intracellular sodium. Alkaline earth nuclei, beryllium, magnesium, calcium, strontium, and bromine are chemically rather similar and essentially form ionic compounds. The exception being beryllium and to some extent magnesium, which has profound tendency to form covalent compounds. Both calcium and magnesium play important role, as you know, in medicine, in various physiological processes. Beryllium is characterized by its extreme toxicity, and organoberyllium compounds have attracted considerable attention. Now, these are not very popular. There are unfavorable properties of alkaline earth. From the NMR point of view, the situation of alkaline earth is not as bright as that of alkali metal due to unfavorable nuclear properties in general. The only useful nucleus in this series is beryllium. Barium has two NMR isotopes, both with large particle movement resulting in extremely large line broadening. Strontium shows much less broadening than barium, but still is not favorable. Then again, transition metals. In this class, the atoms have partially filled D and F shell. A total of 61 stable isotopes are NMR sensitive in this case, in transition metal and lanthanide. However, many transition metal compounds are paramagnetic, and this imposes limitation on applications of NMR to such systems. So they are not very popularly being used. The chemical applications of NMR have employed only about half of the number of these isotopes. And these are some of the properties. And this, and you can see that the disadvantages are inherently present in these properties. Cobalt 59, as I told you, is the highest chemical shift range. It is less sensitive than proton only by a factor of 3. So that is why this was studied in complex compounds from the very early discovery in 1950. Thus putting it among the top 6 nuclear species in terms of ease of detection. However, it has a spin of 7 halves and large particle movement, but the range of chemical shift is among the largest known. Most NMR data come from hexa-coordinated compound, which is diamagnetic. Despite broad lines, several kilohertz for asymmetric coordination, it has been feasible to acquire significant chemical shift. It is essentially because the lines are so well separated. Then there are again very heavy metals, platinum 195, titanium 203, titanium 205, cadmium 130. They all have been studied, and again, these are some of the very, very useful nuclei from the medical point of view also, cadmium, titanium, and this. High sensitivity of chemical shift to structural changes. Small changes in the structure give large shift in the line. So that makes them very useful and easy to detect. Then cadmium 113 again is a promising nucleus for biological application. Coordination chemistry of tin compounds is very rich, very rich information, very useful. Mercury 199 is again a very favorable spin half, natural abundance 17%, and it work started early, and this again is a very, very useful from the chemistry point of view, as well as from the simplicity, easiness of detection, identification, and applications in biomedical. Aluminium again is very useful. It has again a very rich coordination chemistry, and for the coordination chemistry study, it is a very useful. So this gives you an idea of the range of type of applications of various NMR sensitive nuclei other than proton or other than proton and carbon 30. Actually, proton and carbon 30 are the most used nuclei in chemistry, biology, and medicine. But the others have a great potential also, and the present day instrument with the multi-nuclear probe make it relatively easy and less expensive to study for this. Thank you very much.
So do you have any query?
Huh.
So my question is regarding chemical shift.
Huh.
In case if chemical shift is very small,
Yes.
so we multiply with a particular number. We usually call it multiplicity.
Okay.
So is this number is same for every element or different for?
No. It is different.
It is different. How to decide this number?
You see, if you see, go to the equation. Yeah. Yes. There is a factor called gamma.
Okay.
Gamma for each different nucleus is different. And that is what it makes NMR useful. If the gamma would have been the same, you would have seen only one single line, whatever compound you take. Because you know the simple equation which governs omega is equal to gamma h. Field is not dependent on the nucleus or compound. Frequency is not. The only change takes place in gamma, the magnetogyric ratio. That makes it, that is different for different, and that acts as a fingerprint actually. If gamma or this is the same, then it is, NMR is useless from the application point of view.
Thanks.
So you see the versatility of technique, NMR spectroscopy. A number of nuclei of the periodic table can be screened with the help of this technique. And as per your requirement, one can use the proton, carbon, nitrogen. So I hope sir has provided a wonderful overview of the multinuclear NMR. So we have a short break for tea, and after that we will continue with Professor Ruma's two lectures. Okay. So please be back in 15 minutes.
क्या बोलते थे? केड़ी है हैं? हेलो 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 हाँ आ रही है। तब नहीं आ रही है। अब आ रही है। आ रही है, आ रही है। हाँ क्लियर तो आ रही है यार। आ रही है, सर के पास आ रही है आवाज है भाई विक्रांत? आ रही है। विक्रांत कॉपी नहीं की पेन ड्राइव से।
Oh, okay, okay.
दिस इज
Yes,
ओके।
the first one and then the other one we will see. and their importance to studies of chemical and material properties. I want to return to our understanding or developing our understanding of spectroscopy, of NMR spectroscopy. We have briefly addressed the issues of the chemical shift before, and now we want to address the issues of spin-spin coupling or of spin interactions in total, and do that from a probably a little bit more sophisticated point of view than what you find in regular chemistry textbooks, by looking at the interactions in terms of what also allows us to understand solid-state NMR spectroscopy. So we only covered a little bit of the beginning of the spin interactions, and I want to remind you of that slide. We have a spin, which is this quantity here. It's a vector, and that is proportional to the magnetic dipole moment, which is also a vector. And then we want to discuss the interaction of a vector with some other quantity. And interaction then is always specified in terms of an energy. But an energy is a scalar, so it's not a quantity that has a direction and a magnitude, but it's just a number, a scalar with units. So our interaction partner then for a vector, in order to get a scalar, must be another vector, otherwise we wouldn't be able to get a scalar from the product of two. And the interaction is always as expressed in terms of a product. And the most general way to write such a product is to have the vector of the spin multiplied with another vector, but that vector before is sort of rotated and stretched with the matrix. And that is the coupling matrix. So the interaction is really described by that matrix, and so a matrix with a physical significance is called a tensor. So I was always confused as a student, what is the difference between a tensor and a matrix? It's sort of the same thing, except that a tensor has a physical significance, and a matrix is just an array of numbers for the mathematician. And it doesn't need to have a significance. So we call this green part here, we call the coupling tensor. And the types of interactions are classified. I went through them last time. We have the Zeeman chemical shift and radio frequency interaction of the spin vector with some magnetic field vector. So either the applied magnetic field, it's a shielding from the electrons, it's a radio frequency magnetic field. But then we also have interactions of that spin with another spin. And these are called bilinear interactions. And they are kind of the interesting ones for chemical analysis, because they provide us with information on the chemical structure of a molecule by looking at the interaction of one spin with another. And there are two that are really important. It's a dipole-dipole interaction and the indirect coupling. So two types of spin-spin interactions, and I put the quadrupole coupling in here as well, because it goes with the square of the spin. This is what Professor Ketrapal addressed, for instance, with aluminum, nitrogen, and many other nuclei which have quadrupolar spins. In fact, most of them have quadrupolar spins. And these interactions, the quadrupole interaction, can be very high. If we scale, let's say, the interaction energy in terms of frequency, then the quadrupole interaction can be extremely strong compared to the, or relatively strong compared to the Zeeman interaction, typically high field Zeeman interaction, while the J coupling or the indirect coupling and even the dipole-dipole interaction are relatively small. So our next effort then needs to be to understand how that coupling tensor, what does that mean? And that leads me to the discussion of the dipole-dipole interaction as an example for a spin-spin coupling. And the dipole-dipole interaction is, I've chosen because you can imagine it relatively easily. You know, when you have two magnets and you put them together, then they attract or repel each other depending on what the orientation of the two magnets is. And we'll play with that game. We say, we look, let's say, of a CH group, a CH2 group in a molecule. So C12, carbon 12, no spin. Two protons attached to it, both have a spin. So we have two magnetic dipoles connected by the chemical bond, so they have a fixed distance from each other. and they are both exposed to a magnetic field, to a strong magnetic field. And the field is so strong that the two dipoles align in the magnetic field. And this is like two compass needles, one compass here, one compass there. You line them both, will align in the Earth magnetic field. Now suppose you rotate the molecule. What happens is that the orientation of the spins will stay aligned with the magnetic field while the molecule is rotating. If the interaction energy between the two were stronger than the applied magnetic field, then the spins would rotate with the molecule. That's the weak coupling case, okay, or the strong coupling case. But you have to be at magnetic fields which are much weaker than the Earth magnetic field. So here we are discussing the case that the spins stay aligned as the molecule rotates. And now we encounter an interesting situation. I mean, we know from quantum mechanics, which we will do later on, that the spins can be in 4 possible combinations, stable in their eigenstates. They could be both parallel, both anti-parallel, one up, one down, or the other way around. So there are 4 cases. I'm only discussing one there, one out of the 4. And that one case I'm discussing is the one where the 2 spins are parallel. Okay, and now we rotate our molecule. We rotate our CH2 group because it sits on the molecule. The molecule is in a liquid, there's random motion, rapid motion, so the molecule rotates. What happens? So let's figure out, this is our CH2 bond. So here are the 2 spins, and these 2 spins are plotted. We'll consider that these 2, and they, if they are aligned parallel, then they will repel each other because they have the same orientation. Now the molecule rotates, and as it rotates and the molecules stay aligned, then this molecule, this spin will end up on top of the other one. So we will have this orientation. Now the 2 magnets attract each other. And if we rotate further in another direction, again in the transverse plane, they repel each other, and here they attract each other if we rotate by 180 degrees. So we have attraction and we have attracting forces and repelling forces as we rotate the molecule. Now you might ask yourself, what will happen on average if you average it all out? Turns out, nothing. There's no attraction, no repulsion if we take the time average of the motion. And that is a very interesting case. But there's also, if we go from repulsion to attraction, then there must be an angle of the orientation axis of the connecting vector between the 2 spins with respect to the magnetic field at which that the sign changes from attraction to repulsion to attraction. And that angle is plotted in here. In fact, this is just an orbital of the hydrogen atom, and you can see that we have attraction where the color is red, and we have repulsion where the color is blue. And somewhere here it changes, and that's exactly the angle of 54.7 degrees. It's called the magic angle. It's a 0 point of the second Legendre polynomial. And now the question is, how do we end up with the second Legendre polynomial? I mean, we are not mathematicians. So Legendre was a very smart man. He was a mathematician. He could derive that. I don't know how exactly he derived it. I'm not a mathematician myself. But the question is, can we derive that in a pictorial way? As an experimental physicist, that's my background, I like to see pictures to understand something. I want to have some idea to see things and then understand why that happens so. And what I will do is I will try to give you some arguments that lead us to the second Legendre polynomial. You know, why that orientation dependence is there. I mean, it actually tells us if we have that type of coupling and the coupling influences the NMR frequency, then the NMR frequency changes with the orientation of the methylene group in the magnetic field. So if you have a single crystal, and you have the dipole-dipole interaction between the protons and the single crystal, then your NMR frequency will change if you rotate the single crystal in the magnetic field. This is exactly what people observe in solid-state NMR. In liquids, you don't see it, but you have all orientations quickly change between, they randomly and quickly change, so all the methylene groups which we have here as an example will rapidly reorient, and we see an average of 0 for the dipole-dipole interaction. So it doesn't exist in liquids, but in solids it exists. And it also exists when you have media that are partially aligned. So when you put the molecules, for example, in a gel, and then you stretch the gel a little bit, and suddenly there will be a residual dipole-dipole interaction visible that impacts the NMR spectrum. You will see a line splitting because the molecules are partially oriented. And that is a very important tool today in high-resolution NMR spectroscopy to analyze protein structures, for example. You slightly align them to get a line splitting depending on the strength of the alignment, which helps you from the line splitting then to do a better conformational analysis of the protein structure. So the dipole-dipole interaction is not just something that happens to be in solids, but people also make use of it now in liquids by confining the motion of the liquids to some anisotropic environment so that they are partially aligned, and then you have a partial averaging to not completely to zero of the molecular motion, but only a partial averaging and some residual dipole-dipole interaction is left. So let's look at the dipole-dipole interaction as an example. And we start with some very old geometry. We start with drawing a circle. How do we draw a circle? Suppose you only have the sand. Who was the Greek philosopher who drew the circle? Who knows this? I forgot the name. So the old Greeks discovered that, right? You have two sticks. You have a string, you form a loop, you put the one stick in the sand, and then with the other one you go around and draw the circle. So we draw the circle. Now you want to draw an ellipse with the same string. Which ellipse do you need to draw? So you actually need two sticks. You take the same string that first forms the loop to draw the red circle. You put one string here, the other string there. Fix both ends of the string, the same length of the string, and then take a third stick and move it around, and you get the ellipse. That's the blue ellipse. That's the ellipse that matches the circle. Okay, it's the one ellipse that goes along with that particular circle. Now, what we want to learn is the difference between the ellipse and the circle. You may also say, you take a round ball and you squeeze it. You want to know the deformation of the ball when you squeeze it. So, I want to tell you or lead you to the understanding that the second Legendre polynomial describes the most simple deformation of the sphere. And the most simple deformation of the sphere is to compress a sphere to a rotational ellipsoid. So here's a rotational ellipsoid, actually in 2 dimensions only. And we want to describe the deformation, which is sort of that distance a minus b. B is the short axis of the ellipse, and a is the long axis. A is the radius of the circle. Okay, so a minus b is the deformation. So how we describe that? First of all, we have to write down an equation that describes a circle. Here's the equation for a circle. It's a vector for the zx plane. So there's the x component, is the sine beta. Beta is that angle over here, that's the radius of the circle. And cosine beta gives us a projection onto the z-axis. So the corresponding ellipse we can write by a sine beta and b cosine beta. So all we do is we introduce a different half-axis for the z component. We call that b. That's this distance. And that would be a minus b. Now, of course, if we want to sort of average it, and for all different angles beta, we cannot take a minus b, we have to take a minus b squared, otherwise the average would be 0. Right? It would have positive and negative values. So if we introduce, we figure out what is RC, the radius of the circle, minus the radius of the ellipse, squared. And that would be this equation. That's all that drops out. The next thing is that you don't have to go, you don't try to undergo to each individual step. I just want to tell you what we do. So we calculate the square distance from here to here, and then we subtract the mean from it to all angles, which gives us this equation. And then we are pretty much there with a second Legendre polynomial already. This already looks like it. In fact, the factor of 1/2 is missing. And all we need to do is normalize it for the angle beta equals 0, that the whole thing gets to 1. And that means we introduce the factor 1/2 here. because we divide by 2, we have to multiply by 2 over here, and suddenly we have the second Legendre polynomial over here. That's the second Legendre polynomial. It's the deformation of a sphere, the most simple deformation of a sphere to an ellipse. And that would describe the ellipse represents anisotropy, while the sphere represents isotropy. So, orientation independence versus orientation dependence. The most simple way is the ellipse that describes it. So now we say, okay, this describes our anisotropy of whatever it is. It will apply to the dipole-dipole interaction. And we call this the second Legendre polynomial because it's a normalized function. And this we call the principal value. 2/3 a minus b squared. 2/3 a minus b squared is principal value. And we get it exactly when we set beta equal to 0. So you plug in 0 over here, and you end up with this being 1, and then you get that as the principal value. There's another value that ends up in the literature, is so-called anisotropy parameter, capital delta, and that is a minus b squared, and this is just the square separation. So there's a practical interpretation. So those who like math, they say forget about this, like we Legendre, and those who like the pictures and some visual understanding, they look at this graph. Now the thing comes in, and that we derive a second type of ellipse. We want to represent graphically the anisotropy. And we say, okay, for the angle beta equals 0, we get 2/3 a minus b squared, and we call that as the anisotropy parameter. We call that, give it the index ZZ. So for beta equals 0, we get one value. We put in 90 degrees. Then we actually, for 90 degrees, we get minus 1/3 a minus b squared. So we can look at that function along the z direction where beta equals 0, and perpendicular to it where beta equals 90 degrees. And we have 90 degrees in x direction, 90 degrees in y direction. We have two values for beta equals 90 degrees to get the three values for a rectangular coordinate system. And then we do the following. We plot these values, the ZZ value, the XX and the YY value, along an axis, and again draw an ellipsoid around it. So what we have done now, we have represented the anisotropy, the second Legendre polynomial, in terms of an ellipsoid. That's a different ellipsoid than our compressed football, right, which is the American soccer ball, let's say. So this represents the difference between the soccer ball and the football. And this is a representation that is very often used to represent the anisotropy of a spin-spin interaction. And it describes it by three values. We call that the principal values. The principal value is actually the value along ZZ. And where do we go? I go here. And what one can now do is look at a molecule, for example, polyethylene. I'm in polymer science, so I always take large molecules like polyethylene. Lots of CH3 groups connected to form one large molecule, CH2 groups connected to form one large molecule. And you see there's always the hydrogens in yellow, and they are the ones that have spin. Most of the carbons is carbon 12, they don't have spin. But C13 has a spin. So every now and then there's a C13. Every 100th carbon is a C13. So this is what the molecule looks like. So predominantly you will have CH2 groups with a C12 in here. But every now and then there's the carbon 13, and then you have a 3-spin system. Now if you have a hydrogen atom sitting here, then it will definitely see its next nearest neighbor would be that hydrogen atom. There would be a dipole-dipole interaction, what we just discussed. But there will be more dipole-dipole interactions. There will be also interactions from this hydrogen to that one, to this one, to this one, to this one, and further away. There will be a huge network of dipole-dipole interactions. So discussing just two hydrogens coupling is the most simple case we can imagine. You can see that for certain water molecules and certain salts, that you have isolated hydrogen-hydrogen dipole-dipole interactions of just 2 spins. It's a rare case. The most frequent case encountered is that one hydrogen couples to a huge network through space, not only through, within one molecule, but within also to the neighboring molecules, and there's a huge network of dipole-dipole interactions. Well, if we consider just the 2 of a pair, we can now draw in our coupling tensor in terms of the ellipse by which we represent it. And I go back to show you again the ellipse by which this represents the deformation of the circle of the soccer ball to the foot. Of the foot. The soccer ball is the round one, and the football is the compressed one, right? So that deformation represents our interaction tensor. The interaction tensor is represented by that rotational ellipsoid, which is not the original soccer ball anymore. It's a different rotational ellipsoid. It has these 3 values in the x, y, and z directions that you obtain from varying the angle in the second Legendre polynomial. So it represents our interaction, and we can plot that into the molecule. And then in the molecule, this rotational ellipsoid representing our interaction tensor will point along the direction connecting the 2 hydrogen atoms. And you can see immediately as the molecule now also in polyethylene will move. In the amorphous regions, it will move different from the crystalline regions. If I go back to my very first lecture, we had that case. Then that rotational ellipsoid will move, which represents the interaction tensor, will move within the laboratory frame where the magnetic field point in this direction. So we have a complicated case. We have an anisotropy, we have a tensor that describes the anisotropy, and that tensor sits in the molecule, and the molecule moves in the laboratory frame where we measure. And this is what we sort of have to accommodate in our considerations when we want to understand coupling. Now it actually gets a little bit more complicated when we look at the magnetic shielding. Let's take this molecule over here with a ring current, okay? And then there is a ring current, which means it produces a magnetic field in the center pointing this way and on the sides pointing the other way. And this magnetic field will add and subtract to the applied magnetic field, producing significant effects if the molecule is oriented, if the ring is oriented perpendicular to the magnetic field. But if it's just a minor component field of that ring, when it's oriented parallel to the magnetic field, the field of the ring current will be perpendicular to be 0. Will be something in the ppm range, and be 0, of course, will be a million times larger, so there will be hardly any contribution. So the rotation of that molecule will again impact the chemical shift of the hydrogen sitting at the ring. So that anisotropy of the chemical shift now is described also by an interaction tensor, but this interaction tensor is not as simple as that one. Because here we just, the dipole-dipole interaction we can describe by an interaction tensor, which has, is just the compression of a soccer ball to a football. I always have to think which is the round one, which is the elliptical one. But the American football is the one that is the rotational ellipsoid, and the soccer ball is the round one. Because in German they say Fußball, which is football, and that is a round one, so it is very confusing to me. So here we also have to figure out that we have an American soccer ball. Well, we sit on it and it's compressed. And now the long axis and the 2 half axes are all different. So this is a more complicated case. We call that an asymmetry that comes in, and we have to consider that as well. But we will do this in a later step. Oh yeah, this is actually it. So here is the ellipsoid that represents the anisotropy. We have a symmetric anisotropy, which applies to the dipole-dipole interaction, where the z-axis is the principal value of the anisotropy, and they have the x and y axes and they both have the same value. See, in x and y, the width of that anisotropy ellipsoid is minus delta over 2 in both cases. If you then introduce, and that's the second Legendre polygon. Now if you have an asymmetric interaction, anisotropic interaction like the chemical shift, you have to add another term, and now it depends on how you rotate the rotational ellipsoid around its own axis, and that's the angle alpha. So this formula becomes slightly more complicated, and now the two half axes become different. Delta times 1 minus eta over 2 and delta plus 1 minus eta over 2. So that's the asymmetry in there. This is getting complicated. I will not go through all those details, just to point out how things work. And because they have an impact then, and a different impact on the NMR frequency that we finally observe. Now I said the molecules are rotating. They're not at rest when we do NMR. Even not in a crystal, strictly speaking. But suppose we have them in a crystal, and the crystal sits at some orientation in the magnetic field, and only in rare cases will our magnetic field be parallel to the, let's say, to the principal axis of the interaction tensor. Now that would be the case if the CH2 group, if the two hydrogens of the CH2 group will be just on top of each other, the magnetic field will be parallel. But suppose our molecule rotates, the rotational ellipsoid, the interaction tensor will rotate with the molecule. So we have to describe, actually, because we are doing our observations in the rotating frame or in the laboratory frame, we have to consider the interaction tensor not from the frame of the molecule, but from the frame of the laboratory where we measure. So we have to consider what happens when we rotate the interaction tensor in the laboratory frame here is, or the rotating frame in this case. So when we rotate it away from that very simple orientation. In fact, the interaction tensor can be written very simply as a diagonal matrix that has the values of the principal components, which is the anisotropy in z direction, in x direction, and in y direction as vectors arranged next to each other. That gives us the interaction tensor. But it is the interaction tensor in sort of its most simple form. It's diagonal. You say, well, why put in the zeros when you know they are zero? Well, they are not zero when you look at it in a different reference frame. They're only zero when you look at it in the what people call the principal axis frame. When you look at this in that frame. And the values over here that appear on the diagonal are known as the eigenvalues of the matrix. Now you may wonder what that odd word eigen means. Some people say eigen or so. This is some Americans I heard say that. It's a German word. And it actually means self. So it's a self value of the matrix. So something that's like the soul of the matrix. Something that's inherent to the matrix. The inner self. What is it? What is really characteristic of the values of the matrix? And that means you find a way to rotate the matrix with transformations of the matrix, which means a rotational transformation. And the rotational transformation is actually written in here. There's the matrix, and this is a simple right and left a rotation matrix, r to the minus 1 and r. Alpha, beta, gamma are the Euler angles or rotation angles which you need in order to rotate the matrix. So you find a way, actually, this matrix you can transform into a diagonal matrix, and that means you diagonalize the matrix, and the values on the diagonal are the eigenvalues of the matrix. That's the math behind it. It's linear algebra in a way. So if you study linear algebra, you probably can explain that in a much better way than I have done it to you. But I've taken a sort of way that one can visualize that. Hopefully you can visualize it at least a little bit from the explanations I've given to you. So in the laboratory frame, where we do a measurement of, let's say, a powder, where we have many crystallites. Some crystallites will be oriented so we have that simple way of looking at the interaction tensor in its diagonal form. But most crystallites will be at odd angles, so the interaction tensor will be at odd angles and we have to consider all values of the interaction tensor. I mentioned that the way to go from that diagonal frame to the laboratory frame or rotating coordinate frame is a simple rotation matrix. I've plotted one example so that probably you have seen these somewhere. You have done or used a rotation matrix at some point in time. It is just the cosine and the sine functions of the rotation angle, in this case gamma, and that's the rotation in the xy plane where the z-axis stays aligned. So it's it's a rotation around the z-axis so that x and y change. And just for reference, we discussed right-handed rotations. You know the right-hand rule. When you do a rotation of a vector of a quantity, the thumb points in the direction of the rotation axis, and the fingers then tell you which way to rotate. So any pulse sequence in NMR, you can apply that rule and figure out how does the magnetization vector rotate when you use the right-hand rule. And that's consistent. You can also use the left-hand rule if you use it consistently, then you get similar results. Okay, here's a summary. We had this table before with the different interactions. And here's a summary of the different interaction tensors and their properties for the different interactions. Now what I've done is I've written the interaction tensor in the principal axis frame. It's its self frame with its eigenvalues on the diagonal. Now some interactions actually say, this tensor here, these eigenvalues, if you look only at the anisotropy, they always average to 0. And average to 0 means under rotation, thermal rotation, very fast rotation. And in mathematical terms, it means that the trace, the sum of the diagonals, of all the diagonal elements adds to 0. So, and when it adds to 0 means there is no contribution that you can observe in liquids. But the J coupling, you observe in liquids. Liquid state NMR lives, proton NMR benefits from the existence of the J coupling. And that means one has to add an isotropic term, which is always just diagonal, and that for liquid state NMR spectroscopy, this number would be the J coupling. Okay, that's the value of the J coupling, 10 Hertz or whatever you observe in liquid state NMR is the line splitting, which we'll do in a second, the line splitting. And if you transform that whole expression, so you have the isotropic part observable in liquids, the anisotropic part only observable in solids. And the anisotropic part may be symmetric or asymmetric. Pretty complicated stuff. And in the laboratory frame where you do your measurements, then the anisotropic part will have 9 elements, while here and they're related by symmetry, so it's not really 9 elements. And here you will have 3. And the trace will add up to 0, so actually that is only 2 independent elements. And now I've done check marks to tell you whether the or how big. I've written down the isotropic parts for the different interactions. I've written down if the interaction is anisotropic and if it's asymmetric. So the check mark only means it's isotropic or it's asymmetric. And we see that the Zeeman interaction is not anisotropic and it's not asymmetric. So it's an isotropic interaction, and it's governed by the Larmor frequency. It's the most simple interaction. The same applies actually for the radio frequency excitation. We have a rotation around the radio frequency with frequency B1. It's the isotropic part. And chemical shielding is similar to that. It's just a change of the NMR frequency by the chemical shielding, which gives rise to the chemical shift. So that's the chemical shift interaction which we have there. Then we have the quadrupole interaction, which can be anisotropic and asymmetric, but fortunately the trace, the isotropic part, is 0, and this is why we don't see a shift of the NMR frequency in liquids, because the isotropic part disappears. When the molecules rotate rapidly, we don't see the quadrupole interaction. This is why we can observe nitrogen, N14, in liquids, and we only have an impact on the relaxation times, which gives us broad lines. So hardly anybody does N14 NMR. It's very difficult. Most people like to do N15 NMR for that very reason, because N15 has a spin 1/2, as we just have seen, and N14 has a spin 1, So it has a quadrupole interaction. In solids, we will get a gigantic broadening due to the fact that there is an anisotropy and an asymmetry, and the anisotropy is very high. The dipole-dipole interaction, that again has no isotropic part. It vanishes in liquids. We don't worry about it in liquids. Disappears. But in solids we have to look about it. Or when we have molecules aligned so that the anisotropic part is not averaged to zero anymore, because not all orientations are accessed by the random molecular motion in liquids. So the dipole-dipole interaction is anisotropic, but it's not asymmetric. It's a beautiful interaction. It's still simple. And the J coupling actually is nasty. And it's nasty for many reasons. It's beautiful for liquids because these parts, anisotropy and asymmetry, we don't see in solids. We only in liquids we only see the isotropic part in liquids. And that is the J coupling that we regularly measure. When we go to solids, we have an anisotropy parameter, we have an asymmetry parameter, and what makes it really bad, it is so small that it's so difficult to observe. So there are very few studies on the anisotropy of the indirect coupling in solids. So in liquids, we rely on the J coupling, the isotropic part, and in solids, and aligned molecules aligned in some anisotropic medium, we look at the dipole-dipole interactions. These are the two most important ones. Okay. Let's look at interaction energies. Let's look at an example. We have two spins. The two spins couple. And we like to describe them in terms of quantum mechanics of their orientations, parallel, antiparallel, up, down, down, up. So each of them gives us a separate energy, and the energy is described by the magnetic quantum number, or proportional to the magnetic quantum number associated with that state. Now typically, and I hope I'm not I'm keeping you there, the state is described by the product wave function. The wave function is these alphas and beta. Alpha means spin up, beta means spin down. And the product wave function means alpha, alpha, both up, beta, beta, both down, beta, alpha, alpha, beta. I hope it's right. From where I look and from you look, where you look, it's different. So one up, one down, and you know. Okay, so it's shown here. So this is unambiguous. Beta, alpha, beta means the first spin down, the second spin up, and the first spin up and the second down. So they both have the same magnetic quantum number. But they're drawn as having the same energy. That's the approximation, the very high field approximation, where we cannot see that they actually differ a little bit in energy, while that energy from here to here corresponds, let's say, to 100 megahertz. The shift between the two energy levels here is just a J coupling, 5 hertz or 10 hertz. That's why you can't see it. And because it is so small, we are allowed to use that product wave function and do our math in that approximation. It's an approximation what's written there. It's not the exact truth. Okay. And now, so we have these four energy levels. Now we have to figure out, and it's something that bothered me for a long time, why is it that everybody says we can only observe one quantum transitions when one of the spin flips? Why not two? And I think the answer is because we are using photons, quanta of electromagnetic radiations. And the photon has a spin 1. So all we can do is, when we do a direct observation and put one photon in, or stimulate one emission, we can only change the magnetic quantum number by plus or minus 1, not more. So any direct observation requires that the magnetic quantum number changes by 1. And if you want to see a transition where the magnetic quantum number changes by 2, this simple picture breaks down. You have to use a second order perturbation theory in quantum mechanics, and you can see that. Or you cannot use these simple product wave functions anymore. Or if you are at high field, well, just supply 2 quanta instead of 1. What does it mean when you supply 2 quanta? You need more than 1 pulse. That's a simplification. right? You can also use one very strong pulse that also has more quanta than one, but the situation gets slightly complicated there. So let's say we observe only one quantum transition, so let's figure out where they are. There is the alpha-alpha state, there's the beta-alpha state, so the first spin changes when I do a transition from here to here, from alpha to beta, so we have a change of the magnetic quantum number by 1, while the second spin maintains its state. So we can observe that state. The same, we can observe this state, beta-alpha goes to beta-beta, now the second spin changes its quantum number by 1. So that's also observable. Similarly, that transition is observable, and this one. So we have 4 transitions which are observable. We would expect 4 lines to be visible in the NMR spectrum. And in fact, these are the 4 lines that we see. And we call them actually one spin would have, if it were without a coupling partner, we would only see one line. And it would happen to be at the frequency omega A, because it has spin minus 1/2 and spin plus 1/2. These are magnetic quantum number minus 1/2 and plus 1/2. You would that's where you could introduce a transition. So that would appear here. Due to the fact that you have a coupling to the neighboring spin, that line splits in 2, and that is, we call them, for arbitrary reasons at the moment, omega A1 and omega A2. Now the other 2 lines, the second coupling spin has the same effect by symmetry, and it would be at a different frequency if it were by itself, but due to the coupling it splits in 2. Now the question is, why do I use that numbering A1, A2, X1, X2? Well, the sum from here to here, this energy difference or frequency and this energy difference and frequency has to be the same as that energy difference or frequency. E equals H times nu, right? Energy is proportional to frequency. So that total sum energy must be the same as that sum energy, or this sum frequency must be the same as this. So omega A1 plus omega X2 must be the same as omega A2 plus omega X1. A1 plus X2 is the same as X1 plus A2. Okay, they must add up. And so the sum frequency then is actually, we need 2 quanta to go from here, from alpha alpha to beta beta. And this is why that transition is called a double quantum transition. 2 quantum transition. While this one here, it's called a 0 quantum transition, because in the end you have 1 quantum to be absorbed and another one to be emitted, so that the total is 0. Actually, that's a lousy nomenclature, because it's still a double quantum transition.